This section is on equiprobable spaces. Equiprobable space is a probability space in which each simple event has an equal probability of being the outcome. So, for example, if I toss a coin, it landing on heads or tails has an equal chance of happening. Roll a die, or even drawing from a deck of cards one specific card. The equation for finding the probability of any simple event is just k out of n. So k the size of the event, e, and then n the size of the sample space, so k divided by n. And we would denote that with PR of e, probability of the event happening. So for example, the probability of me rolling a 2 on a die, well, there's one side of the die that has a 2 on it, so you would say 1, and then there's 6 possibilities, so 6. Or the probability of me drawing the 10 of clubs out of a deck of cards, well, there's only one exact card just like that, so it'll be 1 out of 52 in a full deck. Here we're going to go back to the coin toss example where we toss a coin 3 times, and the sample space this time is already listed out for us. We're just going to compute some probabilities. So the first one is toss 2 or more heads, and the event here is listed out as well. So heads, heads, tails, heads, tails, heads, tails, heads, heads, and heads, heads, heads. Those all fit the criteria in that description. So that's 4 times that could happen out of the 8 total in the sample space. So you would say 4 out of 8, which equals 1/2, or you could say 0.5 or 50%. Next, toss more than 2 heads. The only way that's going to happen is if all 3 tosses are heads. In that case, it's just one simple event, so we would just say 1 out of 8. Toss 2 heads or fewer. Well, the only way that's not going to happen is if we do heads, heads, heads. So it's all 7 of these. So that would just be 7 out of 8. The first toss is heads. So heads, 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 tails, heads, tails, heads, and heads, tails, tails. Those are all the possible ways that heads could be first. So that's 4 out of 8 again. And that is 1/2. Toss the same number of heads as tails. I think I mentioned this in the last video that this is an impossible event because there's only 3 tosses, so it's going to be uneven. We're either going to get 3 of one and 0 of the other, or 2 of one and 0 of the other, but it cannot be equal. So since this is an impossible event, we would just say the probability is 0, or 0 out of 8, 0%. Toss 3 heads or fewer. Well, if you look up at the sample space, there's 3 heads, and every single other one of those is 3 heads, and I think we listed this event out in the last video as well. So in that case, the probability would just be 1 to represent 100% or whole, like it will always happen. Alright, in our next example, we'll be talking about rolling a pair of dice. It may be easy to think that there would be only 11 possibilities for getting a sum in dice, either get a 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. But it's crucial to understand and remember that not every single sum has an equal chance of coming up. For example, there's only one way I could get a 2, just by 1 and 1, but there's a lot of different ways I could get a 7. So it's very unequal. That's why we list out all 36 of these possibilities, and it accounts for the order of the dice. So for example, a 3 and a 4 would be different from a 4 and a 3. So our sample space is n equals 36, and the probability of each simple event is 1 out of 36. And we're going to use the notation T2 for rolling a 2, T3 for getting rolling a 3, and then T12 for rolling a 12, so on. So let's look at the examples T7 and T11. So if I want to roll an 11, there's only 2 ways I can do that. I can get a 5 and then a 6, or then a 6 and then a 5. So 2 ways, we'll say 2 divided by 36, and that gives us the probability there. So 0.056, so about, if you want to convert this to a percentage, it would be about 5.6%. So pretty small chance. Next, if we wanted to roll a 7, so multiple ways we could do that. 1 and a 6, and then 6 and a 1. We could get 2 and a 5, 5 and a 2, 3 and a 4, 4 and a 3. So the 6 different ways. So 6 out of 36, 0.167. So that's going to be about 16.7%. So much higher chance of rolling a 7 than rolling an 11 when rolling a pair of dice. One of our vocab terms here, tallying, is pretty straightforward. This is just when we write down all the individual outcomes in any event E and tally their number. Next we have a complementary event. So imagine that you're playing a game, and if you win, if at least one of the two, I should say, cards. So one of the two cards comes up as an ace, and that's the event, the favorable event that you want to happen. Otherwise, you lose, and we're going to call that event F. So the two events E and F are called complementary events. The probabilities of these should always add up to 1. So the probability of event E happening is also equal to 1 subtract the probability of F, or maybe the probability of failure. So if the probability of E getting an ace, well, there's 4 aces in a deck of cards, so that's 4 out of 52. So that's your chances of winning. That should be equal to 1 minus all the other 48 cards out of 52. A couple more terms here. Events are independent if the occurrence of one event does not affect the probability of the occurrence of the other. So, for example, rolling one die, landing on a 2, and then rolling it again, it could land on anything else. Just because I rolled a 2 the first time, that shouldn't have any effect on what I roll the second time. Next is our multiplication principle for independent events. So when events are independent, so for example, event E and event F, two separate events, the probability that both occur as the product of their respective probabilities. So pretty much if I want both event E and event F to happen, then I'm going to multiply their probabilities together. So here's an example. A coin is tossed and a single 6-sided die is rolled. Find the probability of landing on the head side of the coin and a 3 on the die. So for the coin, it's just 1 out of 2 for getting heads. And then we're going to multiply that by getting a 3 on the die. So that's just 1 out of 6. So the probability of both of those happening is going to be 1 out of 12. Next example here, a school survey found 9 out of 10 students like pizza. If 3 students were chosen at random with replacement, so duplicates are allowed, what is the probability that all 3 students will like pizza? So the probability that the first student likes pizza is 9 out of 10. The probability that the second one will also like pizza, we're going to multiply because we want all 3 of them. So we would say 9 out of 10. And then for the third student, it would again be 9 out of 10. So that's going to come out to be 729 out of 1,000. So we could write that as a decimal or a percentage, so that would be 0.729, or we could also say 72.9% chance. So pretty good chance that all 3 students would say they like pizza.